Okay, so we finished our resistive circuit analysis, chapters 1 and 2. From this point on, chapters 3 and 4. Chapter 3 will introduce capacitance and inductance. I believe you would be familiar with some of those concepts from physics. Am I correct? Okay, so we'll go over capacitance and inductance. We won't apply any detailed analysis techniques like mesh current analysis or node voltage. This is straight up voltage and current for a inductor and a capacitor. So voltage, current, power, and energy. So we'll talk a little bit about the theory, and then we'll look at the equations that describe the voltage and current for a capacitor and an inductor, and then how to solve for those voltages and currents. In chapter 4, we will look at transient analysis. And transient analysis is so called because, well, actually, let me back up. In terms of energy, what is different about capacitors and inductors from resistors? The name, yes. Yes, but in terms of energy, if you look at the name capacitor, it has the capacity to store energy. And the same thing with inductance. Okay, so inductors and capacitors are energy storage devices. Resistors, no. Resistors will receive the energy, but they will dissipate the energy in the form of heat. Okay, capacitors and inductors also, there is, anytime there's energy exchange taking place, there's always some energy lost due to heat. But more importantly, capacitors and inductors are energy storage devices. They store energy. Inductors and capacitors are complementary of each other. Okay, inductors store energy in an electromagnetic field. Capacitors store energy in an electric field or electrostatic field. Now, we won't delve into the physics of the devices, okay? We are more in the engineering side. So while understanding the physics of it is good, obviously, but we don't have enough time to do that, we will just stick with the engineering side, okay? So we look at the voltage, the current of these energy storage devices. So chapter 3, we introduce the components. We look at the equations for the voltage and current. But the energy can never be instantly received or discharged from these devices, in just an instant. It always takes a certain amount of time, depending on the capacity of these components and depending on the voltage or current that is being applied. Think of it as a bucket. If a bucket is trying to store water, the amount of time required to fill the bucket depends on the size of the bucket, as well as the flow of the water, as well as the dimensions of the pipe. Does that make sense? Right? So again, think of these devices, again, they're energy storage devices. It takes time for it to fill up, and it takes time for it to empty out. So in chapter 4, what we're going to look at is we're going to look at the equations that will describe the rate of flow of the energy transfer. Because the energy cannot be delivered instantly to these devices and cannot be recovered from them instantly, it takes time. And our job would be to calculate the voltage or current at any given point in time during the process of the energy transfer. Okay? Again, the energy transfer taking place from a source, going into the capacitor or inductor, and then sending the energy back out is a function of time. And so we will look at equations that govern that energy transfer. But that comes later in chapter 4. Right now, we'll stick with chapter 3, which is inductance and capacitance. Okay. So again, as I said, these are energy storage devices. And I like to use the analogy of a bucket, energy storage devices. And so it's a bucket of water that is being filled up.
Professor?
Yes.
I don't think you're showing the online your screen.
Okay, let's see. Thank you for letting me know. Let me change. There we go. I'm still on the first slide, so not much annotation yet. Again, it's a bucket of water, and the fluid or the water that's filling up is the energy. And so inductor stores the energy in an electromagnetic field. The capacitor stores it in a electrostatic field. So magnetism plays a very integral role in everything, in most electronic devices that we use today. Okay. Any kind of generators, motors, transformers, cell phones, any kind of wireless device, right? It all runs on electromagnetism. So let me add phones, television, radio, your wireless chargers, anything wireless basically cannot function without electromagnetism. All right, so not starting, but research on this has been going on for centuries. But around the early 1800s, a French physicist by the name of André Marie Ampère, he came up with what is now known as the Ampère circuital law, right? Describing electromagnetism. And then subsequently, there are many other researchers. Let me change this. There are many other researchers who were doing research in the same area. Some of the famous ones I've listed here: Michael Faraday, Carl Gauss, James Maxwell. They developed many of the basic concepts of electromagnetism. Now, always a word of caution when it comes to science. There's always lots of people working on the same stuff or the same topic around the world. It's just that whoever publishes first or becomes famous, their name gets associated with that topic. So that's the case here too. But electromagnetism, what is it? It is basically the magnetic effects that are caused due to a current carrying conductor. Okay, when current flows through a conductor, it causes a magnetic field to be established. Now, inherently, if you take any wire, a current carrying conductor, whether it carries current or not, it inherently has resistance, capacitance, and inductance. Okay, it is an inherent property. Any wire we take, even if it's a 100-foot long extension cable, the bright orange ones, it has some resistance in real life. We could measure that resistance using, very sophisticated equipment. But that resistance does not rise to the level of interference. Meaning, if we take a 100-foot long extension cable and we plug it into a power outlet of 120 volts, we would expect to measure approximately 120 volts 100 feet away. It does have resistance, but it does not rise to the level of interference. Does that make sense? So in the same way, a current carrying conductor also has inductance as well as capacitance, but it is too small to interfere with the normal operation of that conductor. Okay, so if you take this HDMI cable or this USB cable here, it has inductance, it has resistance. If you take an HDMI cable, they're always very short, about 3 feet or 6 feet, not longer than 10 feet. I've used ones which are like 15 feet or 25 feet long. But at that length, the resistance of the cable rises to the level of interference, and the video signal that is being sent by your device does not reach the other end to the display. So you need very high quality cables that actually shield the interference. Okay. So again, a current carrying conductor will always have a magnetic field present around it. So as soon as current passes through a conductor, even without a current, has some inherent inductance. But when a current passes through it, a magnetic field is established. The magnetic field can be described as the magnetic flux lines that pass around that loop. Okay, so sorry, pass around that conductor in a loop. And it's given by the right-hand rule. Okay, so if you hold a conductor in your hands with the thumb pointing outwards, the thumb points towards the line of the current, which is right here. The line or the direction of the current, and your fingers point towards the direction of the magnetic flux lines. Okay, so it's the right-hand rule. So if you hold your right hand out like this with the thumb pointing out, the thumb points towards the direction of the current, and your fingers point towards the direction of the magnetic flux lines. Now, magnetic flux, again, we are not going deep into the physics of things. Again, like, the electric field, magnetic flux, and the magnetic field is made up of photons. Okay, we cannot see them because the frequency displayed is not in the visible light spectrum. Okay, again, without going into the physics of things, this is where we'll stop. Okay, so magnetic flux is present around every current carrying conductor, which establishes a magnetic field. This magnetic field is very, very weak. It is not strong. Again, it does not rise to the level of interference. But if we take, so I'm going to say weak field, and of course, this is the right-hand rule. Right-hand rule. Again, these are just basic concepts before we go into the equations. If we take that same current carrying wire and we form a loop, a circular loop, then the magnetic field lines are aligned, and all of them, again, think of this, the right-hand rule. So magnetic flux lines is going around in a certain direction. And if you form a loop, those lines will all go inwards or outwards, depending on your perspective, and they all go towards the same direction. Okay, they all go out of that loop in the same direction. Now, again, this is weak. The magnetic field is weak, depending on the charge and the amount of current that is actually flowing through that circuit. But it flows outward in the same direction. If you increase the number of loops in this current carrying conductor, the magnetic flux gets aligned or realigned. You have smaller loops or smaller lines right there. Plus, a longer line is also established where the magnetic flux flows in and out of the entire loop. And it kind of represents the magnetic field that is found in a permanent magnet. A permanent magnet has an inherent property of having a strong magnetic field inherently without any external application of input. Okay, so when you take a current carrying conductor and you form multiple loops, you have what is known as a very weak magnet. Okay, again, this magnetic field is similar to a permanent magnet field. Okay, again, very weak. And then researchers found that you could take this current carrying conductor, and if you insert a ferrous material within those coils, you can increase the strength of that magnetic field, because now you have given the flux lines a ferromagnetic material to actually flow through. So it has to do with the permeability of air versus the permeability of a magnetic material. And that is the working principle of an electromagnet. You take a material like, let's say, iron. Steel is basically just iron. Steel, cobalt, which have high permeability, and we'll talk about permeability on the next slide. And you insert it in the middle of the coil. Or insert through the coil. that increases the strength of the magnetic field. Okay, and that is the working principle of an electromagnet. You have a current carrying conductor. When current passes through the coil, the magnetic field that is established, if you do not have any material passing through the coil, it is known as an air core inductor because there is no material in the core. But if you insert a highly permeable material through that coil, then it establishes a very strong electromagnetic field. Okay, and that is the working principle of an electromagnet. Now, any questions so far? Again, this is just a brief, very, very short recap or an introduction to an inductor. And we look at the same for a capacitor also. All right. So establish a current going through a coil, establishes a magnetic field. This component is called an inductor. The symbol is given by a spiral. So you could draw it like this, similar to a resistor, and draw it vertically or any other way. The letter I is reserved for current in electrical engineering. So inductor is noted by the uppercase L. Uppercase L. The unit is Henrys or Henry. Okay, uppercase L. If it's lowercase, it stands for length. Uppercase L in electrical engineering or in general physics notes inductance. Okay. Now, inductors and capacitors can only store and release energy, meaning they can receive energy and they can release it back into the circuit, depending on certain conditions. They cannot, it's not a source by itself. Okay. It cannot generate energy by itself. Let's see. It follows the passive sign convention. So if you have a current direction through an inductor, the point of entry is plus, point of entry exit is minus. So again, same passive sign convention or passive reference configuration. And if you're given the voltage polarity, then the current always goes from high to low, from plus to minus. So again, resistors, capacitors, inductors, all three of them follow the passive reference configuration or the passive sign convention, where the current always goes or flows from high to low, from plus to minus. If you're given a current direction, then the point of entry is plus, point of exit is minus. Okay. One thing about inductance, if the current is constant, then the voltage across the inductor is zero. And we'll again look at mathematical equations where we can describe this quantitatively. But qualitatively, when current changes through an inductor, magnetic field changes, and hence the inductance level is measured with the rate of change of current. So if current changes in an inductor at a rate of 1 ampere per second, and it causes 1 volt to appear across it, we say that the inductance level of that inductor is 1 Henry. Okay, so 1 Henry of inductance level is a coil that has the capacity to hold 1 volt for every 1 ampere per second change in current flowing through it. Again, we take this much further, we get into the physics. And so I always want to avoid doing that. But again, it's just important as a concept for students to know what an inductance is. If current is constant, inductance or the voltage across the inductor would be equal to 0. The current has to change. It has to change. When it changes, it establishes a voltage across it. That voltage level, if it's 1 volt for every 1 ampere per second change in the current, then we say it's 1 Henry. Typical inductors that we use in electrical circuits are very, very small. Okay. I'll take a 5-second pause. Any questions? Any questions at all?
So if there's no change in voltage, then there's no change in like inductance, or there's no inductance.
No. That's not, I know it seems, that's not what I'm saying. The inductance level is measured. So the inductor has a value the same as a resistor, right? It has inherent to the inductor when it's manufactured. But we are talking about the voltage across an inductor. The voltage across an inductor would go to 0 if the current does not change. So once it has received the energy, you apply a 1 ampere current to it. At the beginning, it's 0 amps. Then you apply a current of 1 amp to it. The current is changing, so a magnetic field is established. So a voltage appears across that inductor while it is receiving the energy. But once the current reaches its full level of 1 amp, then the voltage across that inductor goes to 0. And we'll look at that when we actually get to the equations. Okay, I think I wanted to go to the next slide, but we are out of time. So I'll end class here today. If anyone has questions, I'll keep the Zoom window open, and I'm of course available in the classroom. But we'll pick up here again on Wednesday.